All right. So you should be able to see the notes up on your screen now. And I'm just we'll talk through this together and we'll fill things in. If you have access to a printer, it's always nice to kind of be able to print those out, or you can put them on a tablet, but really it's not necessary. You're welcome to handwrite your notes, that's also fine, okay? I do try and get everything up for one unit right at the beginning, so you could print out like the whole unit and then you'll be set for that particular unit. Okay. All right. So one of the things that I like to do is root whatever that we are going to be learning in something that we already know. So you'll see the structure a lot, what we know and what's new. Okay. So we're going to start with what we know. And right here we have this function, f of x equals 2x. All right. So what shape is this when I graph it?
A line?
It is a line, yes, absolutely. All right, so let's pick a few values to put into the table. And I'm gonna say that usually I like to pick sort of a midpoint and then some numbers to the right of it and some numbers to the left of it. And so in this case, I'm gonna start with my midpoint of a 0 value for x. And then we're gonna put a 1 here and a 2 here, because those are the numbers that are to the right of 0. And then when we count backwards, we'll have -1 and -2, okay? So when we want to figure out the values that go with this, all we're going to do is take that x value, plug it into the equation, find the y value, right? So when I plug in -2, what do I get for the f of -2? Yeah, we get -4. All right, so -4. I plug in -1, I get -2. Plug in 0, I'm going to get 0. I plug in 1, I get 2. I plug in 2, I get 4. Right? So all we did, just plug those values in. Now, before we go ahead and graph this, can someone tell me what we do to get from -4 to -2? Like, what math operation gets us from -4 to -2? What do you mean by the 2 dots? Oh, I see, subtract 2. Yeah, so we're gonna subtract. Well, are we subtracting 2? Oh. Yeah, we're adding 2. Okay, so to get from -4 to -2, we add 2. To go from -2 to 0, what do? We add 2. Okay, so plus 2. 0 to 2, I add 2. 2 to 4, I add 2. Okay. Now, some of you gave some other answers. You said divide by 2. And it's not that it's wrong, but we want to find a pattern that works for every pair of numbers, right? And we can't divide by 2 to get every single number here. But if we add 2, then we'll get all those numbers, okay? So let's go ahead and plot these points, all right? So if you were able to print this out or put it on a tablet, you've got your grid right here. If you are handwriting this, no big deal how neat it is, as long as you can interpret your notes, okay? So we're gonna start by plotting off -2, -4, which is gonna be all the way down here, right? And then we're gonna plug -1, -2, 0, 0, 1, 2, and 2, 4. Okay? And it should not be a surprise to us. I believed it was Laura, maybe, who suggested this in the beginning, that yes, it's a line, but maybe even more specifically, this is a linear function, right? So we should get a straight line when we graph it. Okay, so this is a linear function. Tell me a little bit about this function. Does it have a positive slope or a negative slope?
Positive.
It has a positive slope. And then what is the y-intercept? Yeah, the y-intercept is at 0, right? Okay. So that's our basic linear function. We spent probably a good chunk of our high school experience talking about linear functions. But let's take a look at something that's new, okay? So we're going to graph g of x. So g of x is just another function, but instead of 2 times x, the function is 2 raised to the power of x. Now, we're going to make an XY table. All right, so we're going to put our X values in here. And we're going to use the same X values that we used for the linear function. So I'll go ahead and write in the -2, -1, 0, 1, and 2. Okay. Now, for our G of X, we want to go ahead and plug those numbers in for X. Okay. So there are 2 lines here because the first thing I want us to do is just practice writing it with the exponent, okay? So for example, when I plug in 0, it would be 2 to the power of 0. What if I plug in 1? How could I write that in the same structure?
Two to the power of 1.
2 to the power of 1, good. And if I plug in 2, it's going to be 2 to the power of 2. Okay. What about when I plug in -1?
We could write it the same way or as a fraction.
Ah, yeah. So the first step was just write it as 2 to the -1. And then same thing, this one would be 2 to the -2. Okay. So all we've done is just plug in those numbers. But those numbers I think are a little bit harder to graph. So that's why there's the next line so we can practice simplifying with our exponent. Okay. Let's start with the 2 to the power of 2. I think we all know that 2 squared is 4. I think we also all know that 2 to the first power is 2. But what is 2 to the 0 power?
1.
Yeah, exactly, Jose. It's 1. So we're not going to plug in. It's not 0, but 2 to the power of 0 is 1. Okay. What about 2 to the -1? What is that when we simplify it?
0.2.
It is not 0.2, no.
1/2.
1/2. All right, I see 1/2 in the chat as well. Can someone explain to me where we get the 1/2 from? So that 1/2, I think there's a rule about exponents where when we have that negative exponent, it's the same as writing that base to the power, but in the other side of the fraction line. So 2 to the -1 is really the same as 1/2 to the first power. What does that make 2 to the -2?
1/4.
1/4, good, 1/4, okay? So I know the negative exponents are always a little tricky, which is why I wanted us to practice seeing those and simplifying those and not just throw you right into the deep end, okay? But now, let's take a look at the pattern that happens when we go from one y value to the next. So how do I go from 1 to 2? what's one way that I could get from 1 to 2?
Multiply by 2.
Multiply by 2. Yeah. Now, so times 2. Does that still work for going from 2 to 4? Yeah. So times 2. Okay. Does that work to go from 1/2 to 1? Yeah, right? When we double 1/2, we get 1 whole thing. And when we double 1/4, we get 1/2. Okay? So it's different than our linear function because we're not adding the same number anymore every single time. We are multiplying by the same number every single time. Let's go ahead and graph this, all right? So I'm gonna zoom in a little bit. We're gonna plug in the first point. We can plug in, we could do 2, 4. We could do 1, 2, 0, 1, -1, 1/2, and -2, 1/4. Okay. So from seeing those 5 points, we should notice that it's definitely not a line. It definitely curves, all right? And in fact, it sort of flattens out at the left end. Kind of looks something like this, right? And then it starts to get pretty steep pretty fast. Now, this kind of curve that happens when you multiply by the same number every single time to get to the next number, that is what we call an exponential function. All right, so we've got our linear function, which is just a line, and then we've got our exponential function, which is a curve. All right. So, as familiar as we are with lines and linear functions, I want us to be super, super familiar with exponential curves and graphing them and being able to look at an equation and know what it looks like. That's sort of where we're going in this unit, okay? All right, so let's go ahead and move on to the next page, all right? So today we're gonna talk about exponential functions. And we're also going to talk about exponential models, and that's the part that comes in from section 4.7, okay? So exponential functions is from 4.1 in your textbook, but when we get to the next part, which is exponential models, that's from 4.7, okay? But it turns out that every exponential function is of this form, f of x equals ab to the x, right? And as we're going to learn in just a little bit, these letters stand for different things in an exponential model, okay? So let's label a few things here. This a value, all right, the number in the very front, that is the same as your, sometimes people call it an initial value. We can also think about it as the y-intercept. Okay. This b value, we call this the growth or decay constant. Okay, so B stands for the growth or decay constant. The X up in the exponent, that stands for time. Okay, so a lot of our things are going to be growing over time or shrinking over time, and so the time is what the X represents. Okay, And last but not least, our f of x. This whole thing here represents not our initial value, but our ending value. And sometimes people call that a desired value. Like it's the number you're trying to find in the problem, okay? So if someone says, give me an equation for a linear function, I think most people say y equals mx plus b, right? You see a linear function, you think y equals mx plus b. But now when someone says, hey, so we have this exponential function, I want us to think f of x equals ab to the x. Like I want this to be automatic. We know every time we see an exponential function, this is the equation that we're thinking about, okay? So when we talk about exponential functions, there are two kinds of exponential functions. Sometimes we have a situation where the numbers are going up, like we did in the graph that we saw above. And so we're going to sketch a quick picture of that, but that is called an exponential growth function when you sort of start down low and then you go through your y-axis and then it starts to get real steep real fast, okay? So not only do I want us to know f of x equals ab to the x, I also want us to think this is the shape of that curve. So we really want to strengthen the connection between the equation and the picture, okay? But let's label a few things here. And this point right here corresponds to which letter in the equation? Yeah, it corresponds to A. But I want us to be more specific. We want to be mathematically accurate here. We don't want to call this A. We want to refer to it as 0, comma, A. So we want to write that as a coordinate, okay? Now, if the graph starts down flat and goes up, then this is happening when the B value is greater than 1. So if you look in the equation and the B value is greater than 1, the picture is going to look like this. Now there's one last feature about the exponential function, and that is that it has an asymptote, okay? Specifically, it has what we call a horizontal asymptote. Let me write that out for you. This is the horizontal asymptote, okay? Asymptote is a funny word. It definitely has a lot of consonants going on in there, but that is how you spell it, all right? So a horizontal asymptote. And for us, what that means right now is that the curve kind of gets really close to that green line, but it doesn't actually touch the green line, okay? Now this asymptote has an equation. And when we write the equation of this, we're going to write it as y equals 0. Because on this green line, every single point has a y value of 0. Okay? All right, so the reverse of this is you have a situation where things go down in value. That's what we mean by exponential decay. And so in this case, we actually start up higher. We come down through the y-axis, and then the curve starts to flatten out. Okay. Now this point, we can label the same thing. We can still call this 0, comma, A. That part does not change. But our b value in the equation where it says ab to the x, if our b value is between 0 and 1, okay? If our b value is between 0 and 1, then we are going to have a decay. So not just less than 1, it has to be between 0 and 1, okay? Now this curve also has a horizontal asymptote. Okay. And so let's practice writing that out again. I know that there's a lot of vocabulary in math, and I think it's one of those things that the more you write it, the more you see it, the more you use it, the more familiar it all becomes, right? What's the equation of this horizontal asymptote? It's also y equals 0. And Richard, I'm so glad that you wrote it as y equals 0. We definitely don't want to get lazy and leave off the y. Okay, so we want to keep it as like y equals a number, whatever that number is. Okay? So in a nutshell, this is what exponential functions are. Okay, we've got a situation where the equation we want to think about is y equals ab to the x, or f of x equals ab to the x. In our minds, we're splitting it in two different cases. Sometimes it's going to be an exponential growth, sometimes it's going to be exponential decay. And the one thing that tells us which one it is that b value. Okay. All right. Let's finish off with a little talk on domain and range. I think those are sometimes scarier than they need to be. But we're also going to talk about some notation that might be important for us, okay? So in looking at the two pictures that we have here, are there any x values that are missing from the graph? No, there are no x values that are missing, right? So what we want to say for the domain is that we can put in any number we want for x. Okay? So the way we say that is we say parentheses, the smallest x value would be at negative infinity. Okay. Oh, that's kind of an ugly infinity. Let me try again. Negative infinity. Okay. And it goes all the way, so the comma means everything in between, to positive infinity. And we're going to close it with a parenthesis. Right? This right here is a notation that we use a lot. It's called interval notation. The smallest value is on the left, the biggest value is on the right. So when you see on some of the quizzes, it says, I want you to write your answer in interval notation. This is what I'm talking about, okay? Now, some of you in high school or in your previous classes might have also heard that this is the same thing as all real numbers, okay? So all real numbers is the same as from negative infinity to positive infinity. Or for those of us who are like wanting to use some fancier math notation, there is a symbol for all real numbers, which is a capital R, but it's like a script R. So the way I write that is I write it like a double line R, and that's my symbol for all real numbers. Okay, so all three of those are the same, but I want us to be using interval notation because that comes up a lot not just in this class, but specifically when we start to hit Math 150, like Calculus 1, and definitely in Calculus 2 comes up a lot. So I want us to really start to set the stage for being familiar with this notation. All right, so that is the domain. What about the range? Are there any y values that are missing from both our exponential growth and our exponential decay?
0 and negatives.
Yeah, zero's not part of it. The negative numbers are not part of it. Perfect. So the way we write that is we want to talk about the smallest y value it could be, which is 0. Okay. And it's going to go all the way to positive infinity with the parentheses. Okay. You might also see this as, if you're getting really fancy, sometimes people call this the real numbers, but the positive ones. Okay, so that's something that you might see in some textbooks. It's not very common, but we're going to stick to the interval notation. Okay. And then the last question here is there an asymptote? And yes, there is. We talked about that green line. So we have a horizontal asymptote at y equals 0. Okay. So when you are studying for next week's exam, because that's right, we have an exam next week, this is probably a good way to center yourself on the concepts that we're going to be having on that exam and making sure that we know the different parts of the graph. All right, Eric's got a question. Why is 0 included in the range if it never hits it? Okay, so really good question. When we use the parentheses, it means it never gets there. If we wanted to include 0, we would have written bracket 0, comma, infinity. Does that make sense, Eric? Yes, okay. And we're not using I see a square box, like a rectangle, but I think you meant to type something else in. Can you tell me what you were trying to type? Oh, so the bracket, because when we use the bracket, it means we include 0, but our graph gets really close to that green line, but it never actually gets there. Does that clarify that? Okay, cool. So let's put an X through that so we know for the exponential ones, we don't want to use a bracket. Okay. Okay. So we're going to move on to exponential models, because one of my favorite things about this unit is that it actually is math that you use again in your life. There are so many things that, you know, whether you're going to be a STEM major or not, exponential models are really valuable for every single person, okay? So when we think exponential, what is that equation that we want to remember again? Yep, f of x equals ab to the x. Great. So we're going to write that again. F of x equals ab to the x. Okay. I'm a firm believer that writing, like that act of writing, helps connect the content to your brain, makes it a little bit stickier. Okay, so that's why sometimes I have us write things again. It's sometimes why I ask you to say things again, because that repetition all helps it become a little bit stickier for you. Okay, so we've got our a value, which is our starting value or our initial value. And we said that B was our growth if B is greater than 1, or it is decay if B is between 0 and 1. Okay. Now we're going to see a lot of percents in the word problems that we use or that we complete. B does not equal the percent that they give you in the word problem. Okay. B does not equal the percent they give you in the word problem. But let me give you a handy dandy little formula so that you can use the percent to find the B. Okay. So if you want to find B, if you know what the percent is, you can use the following formula. B equals 100 plus or minus the percent divided by 100. Okay. Now this is not like the quadratic formula where you add and then you subtract and you get 2 answers, okay? You're gonna choose. So if it is growth, let's see if we can use some highlighter here. If you have a growth situation, you're gonna choose to add the percent to 100. However, if you have a decay situation, you're going to choose to subtract the percent. Okay? So growth means add, decay means subtract. And you don't even need to move any decimal places here. You just need to pull the number that is the percent. Okay? X represents the time that we have. What color did I use here? Pink. All right, and then we've got our ending value as our y. Okay. Now, in the short span of 10 minutes, we've seen this equation twice. That's how important it is. If this is like the one thing you put on that reference sheet for next week's test, this is important. Okay. All right, so now let's talk about how to use this. So example 1, true story. My friend Erin, actually, she wanted to buy a new truck. She likes the Toyota Tacoma because it's a little smaller than like some of the other pickup trucks. But she was thinking about purchasing this Toyota Tacoma, and the sticker price was about $36,000. Okay. Now, every time you drive your car or your truck or your vehicle, the moment you drive it, the value of that goes down. And most cars, okay, with a few exceptions, like some of the more classic cars, all right, if you're into like classic cars, those values definitely go back up. But in general, cars lose value over time, okay? So we have a fancy word for that here. It says if her truck depreciates by 17% each year. Okay. That is, I did actually look up that number. That is about the percentage that Toyota Tacoma loses its value for. So different cars have different percentages. Some of them, the percentage is a little bit smaller, and some of them lose their value really quickly. So that's like an added bonus when you're thinking about like shopping for a vehicle. It's probably better to get one that doesn't lose its value as quickly so that you can hold on to that card for a longer period of time, okay? But let's take a look at this first question. It says, if her truck depreciates by 17%, oh, there's that percent, by 17% each year, write a function that models the value of the car, okay? As soon as I see percent, I'm thinking f of x equals ab to the x. I see the percent in the problem and automatically I connect it to, hey, this is an exponential function. So in order to write my equation, I need to fill in a value for a, and I need to figure out a value for b. And those are the only two numbers I need to plug in. Okay. So f of x equals a, according to our notes from earlier, is the starting value. So what is the initial value of her truck?
36,000.
36,000, you got it. And finding the initial value is that easy. It's usually given to you right there in the word problem. So don't overthink that, okay? So 36,000. That's my A value. Now for the B value, we typically open up a set of parentheses, but we don't have to, okay? But we typically open up a set of parentheses. And what we're gonna do is we're gonna use this formula for B to help us find the value given our 17%. So I know it's 100 plus or minus. In this case, we know it depreciates, so we're gonna pick minus. So 100 minus 17. And then to make it into a decimal, that's why I divide by 100. Close that, put it to the power of x. Let's clean this up a little bit. F of x equals 36,000 times, when I do 100 minus 17, and then I divide by 100, what value do we get? Yeah, 0.83, okay? So 0.83 to the power of x. This is our equation that models the value of the truck, okay? Are there any questions about how we wrote our equation? How we got the A value, how we got the B value? So the second part to this question is find the value of Aaron's truck after 7 years. So I don't know about you folks, but I like to hold on to my cars for a while. If I'm gonna buy a car, I like to make sure that I drive it for a really long period of time so that I don't have to keep paying for a new car or like a newer car, okay? So if I wanna find out the value of her truck after 7 years, where do we put the 7 in our equation?
On the x.
Yeah, we put the 7 up where the x is, okay? So what that's gonna look like is f of 7 equals 36,000 times 0.83 to the power of 7, okay? Now, when we plug this into our calculator, so this would be a calculator question, okay? We're gonna get a number, and a lot of times we end up with a lot of decimals in our answer. How many decimal points is a good number to round to for this particular question. I see someone has rounded 2 decimal points. Yes, perfect, 2, because we're thinking about money, right? So we want to go to 2 decimal points, right? So if you have a calculator, you can type this all in at once, right? We want to start to move beyond like plug in one number and then round it and then multiply it later. If you can, try and plug it all into the calculator at once, and then I think we've got one answer and that matches mine. So you should get, don't forget the units, numbers, or dollar sign rather, not a number sign, 9768.98 cents. Okay, so the value of her car in 7 years is a little bit less than 10,000. All right, any questions about example 1 here? Okay. Let's go ahead and take a look at example 2. Okay, so I think that buying a car is something that hopefully we have a chance to all do at some point. It might be a real big goal for some of us, like I want to have my own car. And another thing that I think applies to a lot of folks is retirement. And maybe that's really far away for some of you, or maybe closer for some of you, I don't actually know. But retirement is something that at some point we hope that we don't have to work a full-time job forever. And that if we wanted to retire, that also means that we don't have any income, and we kind of need to think about saving up for how we're going to pay for our living costs. So sometimes when you have a full-time job, there are companies out there that will contribute towards your retirement account. So your company that you work for will pay for some of your retirement. And it depends on the company. It depends how much they're going to pay. But that is tied to a job. But there is something called an individual retirement account. So an individual retirement account. And you might hear that word shortened to an IRA. And so when folks say IRA, what they mean is that retirement account that you're saving for yourself. So it's like a special kind of savings account where you are saving for your retirement. Okay. Now, every year you can put money into your own IRA. So no matter how old you are, you can start to save for retirement. Now, I know that when I first started working full-time, after I finished school, I was like, someone's gonna come and ask me to like put my own money into this retirement account, and I'm like 22 years old. Like, why do I want to start thinking about that now? And like, how much can I put in? Can I put in like $100? Is that okay? And the money folks that I was talking to were like, well, the most you can put in every year for yourself is, right now, it's $6,000. And I was like, $6,000, that is a lot of money. And right now, I just finished school, like I have loans to pay. I don't have $6,000 to put aside. Now, you don't have to put in all 6,000. You can put in 100, you can put in 200, you could put in 3,000, you could put up to 6,000. So you don't have to put in 6,000, okay? But what happens is your money sits in this IRA, or individual retirement account. And on average, if you are someone who's interested in like investing in the stock market, on average, if we're talking like over like 20, 30, 40 years, your investments usually give you about 6% back. Okay, so whatever you put in, it gives you 6% more than what you put in. So let's take a look at this question. Let's say we get through this STEM core program, you get your transfer to the 4-year school, and then 6 years from now, 5 years from now, you are in this rock star job of your dreams, and you're like, oh, remember the first day of class and Judy told us about this IRA thing? Maybe I should do that. I'm feeling pretty good about my paycheck, and I want to put $6,000 towards my personal retirement account that first year that I work. And let's say you do that, and then let's see what our equation is going to look like. Okay, so 6%, I see the percent automatically. I'm thinking f of x equals ab to the x. I see the percent, I'm thinking exponential. Just like with the truck problem, I have to find my a value and I have to find my b value. I don't want to see anyone put the 6 in for the b. You got to do something with it first, okay? What can we put in for a?
$1,000.
6,000, exactly. That is our initial amount, our starting value. So we can replace a with 6,000. Let's set up our parentheses for how we are going to find b. So we're going to do 100. And is it going to be plus or minus?
Plus,
Plus. And how do we know?
because it's increasing 6% per year.
Yeah, we sure hope we are investing in a situation where our money's growing, right? We don't ever want to invest in a situation where that money is shrinking. So we're going to do 100 plus 6, and then we'll divide it by 100 to get it into the decimal, and put the x, because we don't want to forget about the exponential part. And when we clean this up, we'll get f of x equals 6,000, 1.06 to the x. Okay? So with this equation, we can figure out how much our money is worth at any point in time, right? So let's say you're in this first job, right? You found your dream job, you put $6,000 into your IRA the first year because Judy said to, and then you forget about it. You forget about this account for your entire career. You forget about it for 30 years. You don't put more money into it. You don't take anything out. Let's see how much your account is worth after 30 years, okay? So I'm not asking you to put in 6,000 every single year. I'm asking you, do it once and let's see what happens in 30 years. So we're gonna take our equation, 6,000, whoops. But instead of x, we're gonna put 30. 30 years is how long you forgot about this account. 1.06 to the 30th power. Now we're still talking about money here, so let's round to 2 decimal places. How much is this account worth in 30 years? Yeah. Got about 34460.95. Well, that's a lot bigger than $6,000. You put in $6,000 and you made almost $30,000 without having to do anything. I think sometimes the idea of saving for retirement can be really scary for us. We all have a lot of costs that come up, and sometimes we feel like we don't have $6,000 to put away, and that's fair. But if you put in even a little bit, especially at the beginning of your career, that way you give it more time to grow. The more time you give your money to grow, the more money you're going to have. Okay? All right, how do you write an equation where do you put in the amount every year? So if you want to find out how much it's worth after 1 year, you plug in 1 for X. If you want to find out how much after 2 years, you plug in 2 for X. Does that make sense? Is that what you're asking? Oh, okay. I see what you're saying. Yeah, so like if you maximize it, so then what you can do is like you take your new amount. So if you plug in 1, right, you get the amount after 1 year. And then if you add another 6,000, that will give you the new amount that you'll plug in for f of 2. So you'll have a new starting value. But rather than do this by hand, if you go online and look up retirement calculators, there should be calculators out there that kind of help you figure out how much you're doing. But if it's within your financial means to maximize your IRA every year, that's definitely important, right? Now, that being said, with your retirement accounts, if you put in more money at the beginning of your career and then less money later, it's still, you're giving money more time to grow. It's still worth investing in. I think it would end up being some sort of recursive situation where we're gonna have to take what we get and then plug it into the new one. So I think that equation might not necessarily work. One last benefit about the IRA, and I'm not a financial expert, I'm just sharing a little bit of what I've learned over my years of trying to figure out what it looks like to hopefully retire one day. The other benefit to this is when you file your taxes, the government usually gives you a little bit of a tax break because you're saving for your retirement. So you put this money away, and sometimes they either pretend like you earned $6,000 less, so you might be in a lower tax bracket, or they'll give you some sort of tax credit in your refund, and they're like, hey, good job for saving for your own retirement, so we don't have to pay for you later. Let's give you a little extra bonus right there. So it's not just that your amount will continue to grow, but in the meantime, you'll get more back on your taxes, or you'll pay less in taxes by showing the government that you are actually investing in your future. Okay. All right. Let's take a look at another common type of example. Okay. So for those of you out there who might be like bio majors, you're thinking about going into something in the STEM field, but maybe not like pure chemistry or pure math, but biology definitely has applications as well. So manatees, which are super cute, if you look up baby manatees, oh my God, so adorable. But they have recently been removed from the endangered species list, which is pretty cool. So if there are currently 13,000 manatees worldwide, and its population is growing by 1.5% each year, write a function that models the population of manatees. Okay. And then, as a part B, determine how many manatees there will be in 5 years. Right? So we see the 1.5%, and we are automatically thinking f of x equals ab to the x. All right, so come test day, I don't even want that to be a question for you. I want you to know automatically, all right, I see the percent, here's my equation. And we need to find our starting value, which is pretty straightforward. And we need to find our b value, which usually takes a little bit more work. So if we write our equation, we'll get f of x equals 13,100, and let's see, this population is growing, so 100 plus 1.5 over 100, and we're going to raise that to the power of x. And we're going to clean this up so we can use it in part B. F of x equals 13,000 times 1.015 to the x. Okay. Now, to determine how many manatees there will be in 5 years, everywhere we see the x, we're going to plug in 5. Now this time, when we plug this in, we're going to get a lot of decimals. How many decimal points might be appropriate to round to here? Yeah, 0, because we're looking at living animals, right? So we actually want to think we're going to round down to the nearest whole number, okay? So when I type this into my calculator, I get about 14,004.69 and a few more decimal places. But if we're thinking about how much we should round to, we're not going to round up, but we're going to sort of just cut off the decimal and leave it as that whole number. Okay. So applications in biology and in your financial world. So we could talk about population of people, even in like if you're studying some sort of social science, that's also applicable there. Some people use this to look at cell growth, like in a lab when you put cells on a petri dish and you kind of grow them to see what's happening. It's also important there to think about the population of cells, okay? And one last common use of exponential function, okay? Saved a good one for the last one. So in this case, we're looking at maybe a specific application to something we might use more in the medical field, okay? So I don't know if any of you have ever had like an MRI or a CAT scan, but if you have, you know that usually for some of the imaging techniques out there in medicine, you need to inject a certain isotope so that it shows up on the imaging. So when folks need to get a kidney scan, they actually use Hg197 to help show what they're looking for in a kidney scan, okay? But this thing in the box is the isotope that we're looking at. And sometimes I actually go ahead and cross out the number that's attached there because we don't actually need this number anywhere in our equation. It's like a distractor number, okay? So I find it helpful sometimes, like I don't need to find a place for the 197, so I just kind of cross it out. Now, it has a half-life of 64.128 hours. Now, here's what a half-life is, all right? So a half-life means that if you start with a certain amount, after 64.128 hours, you're going to have half of that amount. And in another 64.128 hours, you're going to have half of that amount. So you're going to keep losing what percent?
50%.
Yeah, you're going to keep losing 50%. So as soon as you see half-life, you're almost thinking lose 50%. Right? So this one's a little bit trickier because the percent is not obvious in the question, but we kind of have to know that when it says a half-life, it means lose 50%. All right, so let's write our exponential decay function here. We've got f of x equals av to the x. We plug in our numbers. Instead of our a value, we're going to put 12 because we start with 12 milligrams. That's how much they need in order to be able to see what they need to see on the kidney scan. Now, we got to find our b value. So we can open up our parentheses, have 100. It's losing 50%, so minus 50 over 100. Now, before we put in our exponent, okay? The exponent here we want to put in is how many half-lives. What that means is we don't just put an x up here. We're going to put x divided by the half-life. All right? So if I say, like, how much is left after 64.128 hours? How much is left from our 12 milligram sample?
6.
Yeah, we have 6. And if I wait another 64.128 hours, then I'm going to have 3. So we need to incorporate that half-life into our equation, okay? And that's where we put it. And we can do the same thing where we clean this up so we have a nicer equation to use for the next part. It'll be 12 times 0.5 to the power of x over 64.128. Okay. All right, so let's find the amount remaining after 72 hours. Is our answer going to be bigger than 3 or smaller than 3? Yeah, it's going to be bigger than 3, right? Because it's more than 1 half-life, but not 2 half-lives. So it's somewhere between 3 and 6 should be our answer. Now, in this case, I would say it's a little bit less clear how many decimal points. So let's, for this one, round to 3 decimal places. Okay. And when we do that, I believe we get 5.510 milligrams are left after 72 hours. Okay. All right. Any questions on these exponential models? These are actually my favorite kind of word problems because they all kind of follow the same pattern. So if you're someone who doesn't really like word problems, I think these may be a little bit less bad than some of the other word problems you've encountered, okay? All right, so let's finish off 4.1. So this part goes back to 4.1, okay? All right, so sometimes we want to write an equation, but they don't give us percents. Okay, so let's read through example 5. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. If the deer population is increasing exponentially, write an algebraic function representing the population of deer over time. Okay. And let's kind of scroll down and take a look at number 6. It says, find an exponential function that passes through -2, 6 and 2, 1. Okay. So we're actually going to start with question number 6 here. Okay. We're gonna, both of these questions ask the same thing, only one of them has more words and the other really, I think, helps us unpack that process. Okay. So one of the first things that you want to do when you're looking at these kinds of problems is you want to write the information as 2 coordinate points. Now, in number 6, they already did it for us. So we've got -2, 6 and 2, 1. Okay. But in the word problem, like number 5, they don't give that to you as a coordinate. You have to write it like that. Now, the second step we're going to do is we're going to sub both points into f of x equals ab to the x. So we're going to have 2 equations. Right? When I take the point -2, 6, which one of those point numbers goes in for x and which one goes in for f of x? Yeah, the first one is the x and the second one is the y. Okay, so when I rewrite this, it's going to look like 6 equals ab to the -2. How do I write the second point into the equation, into a separate equation? What does that look like? Yeah, 1 equals AB squared. Good.
Mm.
1 equals AB to the power of 2. Very good. All right. So this is where we've subbed both points into our equation. Right? So step 3. We're going to go ahead and isolate A in both equations. So isolate just means get the A all by itself in both equations. We're going to set them equal, and we're going to solve for B. So if I take the first equation and get A by itself, I'm going to divide both sides by that B to the negative 2. So that's going to give me A equals 6 over B to the negative 2. When I do the same thing with the 1 equals AB squared, I'm going to get A equals 1 over B squared. Okay. Now, I'm going to set them equal to each other. So I'm going to take this, and I'm going to set it equal to this, because they both equal A. So we get 6 over B to the negative 2 equals 1 over B squared. How do we solve for B at this point? What are some ideas that folks have on how to simplify? So one of the things that I hope you folks will help me do is understand where you're at a little bit better. If people aren't sure, it's okay to say, I have no idea where to go from here. Or if you do have an idea, I'd love to hear your voice and think about like how to work about it. So let me ask that question one more time. We're trying to solve for B here. Do people have ideas on how to get B by itself, or are we totally stuck? Where are we at? Did we divide? I see square root. Divide by 6. Okay. So when we are thinking about dividing, like 1 over B squared, there's not really anything I can do to simplify that. And the same thing with the other side, 6 over B to the negative 2, I could maybe clean that up, but one of the things that I find really useful, when I see a fraction equal to another fraction, I'm like, yes, because when I see a fraction equal a fraction, I can actually go ahead and cross multiply, okay? Or I think like David is kind of saying, multiply each side to find a common denominator, right? So we're actually going to go ahead and cross multiply here. So we have 6 times B squared. So that's going to give me 6B squared. And it's going to be equal to 1 times B to the negative 2, or B to the negative 2. I find that sometimes cross multiplying at least gets rid of the fraction, and then it makes me maybe feel a little bit more able to solve the equation, okay? I'm gonna try and get all the b's on one side. So in order to do that, I'm gonna go ahead and take this b to the -2, I'm gonna divide it to the other side, okay? At the same time, I'm gonna move the 6. How do I move the 6 that's on the left-hand side to the right-hand side? Yeah, you divide it. Good, good. Okay. So I'm going to get b squared over b to the -2 equals, if I divide by 6, what's on the right-hand side? One over 6. Very nice. 1/6. Okay. Now, we learned once upon a time in our academic careers how we can combine exponents like this. Does anybody remember how we can, what we do when we have the exponent on the top and the bottom? Like, how do we combine that into a single exponent? We subtract the exponents. Okay, good. So we have 2 minus -2. What do we get? 2 minus -2. Let me say that one more time. 2 minus -2.
4.
Yeah, it's gonna give us 4, okay? So when we subtract these exponents, we get b to the 4th. Because 2 minus -2 turns into 2 plus 2, which gives us 4, okay? So b to the 4th equals 1/6. All right. We got one last step to get b by itself. How do we get rid of that 4? Yeah, exactly. We're gonna find the 4th root of both sides. So that's gonna look like b equals, and when I wanna take a 4th root, it looks like a square root, but I have to write a little 4 there before I write the square root, okay? So that doesn't say 4 times the square root, it says the 4th root of that number. Now, let's type this into our calculator. How in the world do we type that into a calculator? I think everyone's calculator is a little bit different, okay? But so one button that's really important for us should be one that looks like a caret, okay? So if you have a calculator handy, I want you to type in this, 1/6 in parentheses to the caret, that's to get it up into the power of 1/4. So the power of 1/4 is the same as taking the 4th root, right? So the power of 1/4 is the same as taking the fourth root. So when we type that in, we should get a b value of 0.639. All right, how we doing out there? I know there was a lot of algebra in this one part. Are there any questions about how we got the setup, how we solved for B? We're not quite done yet, but I do want to pause and just make sure that we're feeling okay about where we're getting numbers from. Okay, good questions. First one, how do we know when to cross multiply? Usually when I see a fraction equal a fraction, I'm like, yes, cross multiply. Okay, so if you see a fraction equal a fraction, that's a good time to cross multiply. Richard, to your question, how did you know to divide b to the -2 first and then the 6? I think it was more a goal of let me get all the b's on one side and then let me get all the numbers on the other side. So you could have moved the b squared to the other side. That also would have worked. All right, so let's see where we've been and what we still need to do. We wrote our information as 2 coordinate points. We did step 2, where we subbed both points into f of x equals ab to the x. And we isolated a so that we could set them equal to each other and solve for b. Now, anytime we write an exponential equation, we don't just need b, we also need an a value. So that's what step 4 is. We're going to solve for a. All right, now the good news is if you have a number for b, you have not 1, but 2 equations you could choose from to plug the b in and find your a. Like it's already solved for you, okay? You literally just need to plug it in into your calculator and you're all set to go. Now, do folks want to use the a equals 6 over b to the -2 or a equals 1 over b squared to find your a? Any preference, first one or second one? Yeah, I think the second one, all right? So 1 over b squared. So I'm going to say a equals 1 over b squared, which is a equals 1 over 0.639 squared. And that should, let's see what that gives us. 1 divided by 0.639 squared. 2.449. Okay. All right. Home stretch. We just got to throw everything into the equation so that we answer the question. Step 5. We are going to put a and b into the equation. So what I mean by that is f of x equals 2.449 times 0.639 to the power of x. So the a value that you got and the b value that you got, you just need to plug them into the equation. Okay. Now looking at this equation, can someone tell me, is example 6 a growth situation or a decay situation? It's a decay situation. How do you know that? Folks who answered and answered so quickly, how do you know it's decay? Be more specific, what's less than 1? Yeah, the B value is not just less than 1, but it's between 0 and 1, right? So we know based off of that, that this means that it is a decay situation, okay? And so in our brains, we want to think about that graph that's getting smaller and smaller as we go, okay? All right. So we're going to take these 5 steps and we're going to go back to example number 5 and give that one a try, okay? So write the information is 2 points, sub both points in, isolate A, solve for B, solve for A, and then put everything into your equation. All right, so I'm not going to write out the steps in words, but I'll just put a 1 so that that matches the 1 below. But if I were to write things as points for this problem in example 5, how could I frame the points? Or what would be the coordinate?
Would it be 0, 80 or 0, comma 80?
Can you tell me why you're saying 0, 80 and not 2006 and 80?
Oh, because it's the starting point. So X would be 0 and then Y would be 80.
Yeah, okay. So some people like to write it as like the year and then the amount, okay? But I would say that for our purposes, we really want to think about like what the starting date is, and we count that starting date as 0, okay? So if we're starting in 2006, we're going to call that the 0 year, or the beginning of time for when we started counting whatever we're counting, okay? So we've got 1 point, 0, comma 80. And I know my second point is something comma 180. What's the X value? It's 6, exactly. Because 6 is the difference from 2006 to 2012, okay? All right, so we've got our 2 points. Our next step is to substitute them in to the equation. So we're gonna get 80 equals AB to the 0, and 180 equals AB to the 6. Ah, okay. Can you explain your thinking a little bit for us here? Ah, how did you know that 80 is the A value? Because that's how many deer there are initially, right? Okay, I'm so glad that you brought this point up, because let me just scroll down for a moment. All of this was a whole lot of work, right? And I think one of the hard things about math is we have one way of doing something, and then we have another way of doing it. And we oftentimes learn a lot of different methods, and then it becomes a question, well, how do I know which method to use? Okay. So here's the deal. In example 6, I showed you the long way, and it works for every single set of 2 points, okay? So those 5 steps will work every single time you have 2 points. But when we take a look at sometimes, not always, sometimes they give us the A value. And what they're saying is, if you have A, the only thing you need to do is find B. So don't spend too much time working on this problem if we're going to give you information that might make your life easier. Because this 80, I can go ahead and plug in right for the A, right? So let's be clever about this. And in this step, we can say if we have A, okay, then we can plug them both into the same equation. We'll get 180 equals 80 times B to the 6th. You don't have to do it this way. The other way that we did it, the longer way in example 6, will work. So we don't have to do it this way, but it doesn't save us a little bit of time. Okay. In this equation, how do we get B by itself? Divide by 80 on both sides. I love it. All right, so I'm going to do 180 divided by 80 equals B to the 6th. And then perfect. We're going to take the 6th root. So B equals, I could write 180 over 80. If I wanted to write it as a power, what would the power be? 1 over 6. Yes, perfect. 1/6. Okay? All right, so let's put that into the calculator, see what we get. And let's round to 3 decimal places. Whoops. So we'll get 1.145 as our B value. Okay. All right. And we don't need to do step 4 here because we already found A. So we can skip to 5 where we just write our full equation. When we do that, we'll get f of x equals A, which is 80, times 1.145 to the power of x. Okay, so a little bit less work, only works when you're already given your A value. All right? Otherwise, you got to do this longer way to find B and then find A. Okay? All right, let's do one last example here. We're going to find an equation for the exponential function graphed below. All right? So in the past, we said, number 1, find 2 points. All right? So what would be some good points to use here? negative 1, 1, 3, comma 4. I like those. So we've got negative 1, 1, and 3, comma 4. Okay, you could certainly use those 2 points. Someone else give me a different pair of points that they could use. One, comma 2, and 3. Good. 1, comma 2. And 3, comma 4. That's another option. Negative 3 and 0.5. Are we sure about that point? I'm not sure that we can assume that one. How come no one wants to use 0, comma root 2? Ah, okay, one person does. All right, so here's the deal. I know there's a square root here, and sometimes we look at square roots and we're like, I don't want to use it. But in this case, root 2 is actually our a value. So root 2, this is a. If we use this as one of our points, then we only need to find b. It's a much shorter process. So is this okay? Absolutely, that's okay. Can we use the second set of points? Absolutely. I know someone had said negative 3, comma 1 half. And I forget the other point that they said. And 1, comma 2. Okay. I would maybe stay away from that one because I don't know that this is exactly at 1 half. Does that make sense? So I would maybe not use this one because I'm not sure if that graph is exactly crossing at 1 half, okay? But if this were me and I was looking to minimize the amount of work that I'm doing, I would actually use 0, comma root 2 and any of the other points that they give me, okay? So let's try using 0, comma root 2. And I usually like to pick smaller numbers or 1 if I can. So I'm going to choose 1, comma root 2 as my, or 1, comma 2 as my other point. Okay. All right, so we can kind of skip to step 3 because we're going to use a to find b. So we'll get 2 equals a times b to the power of x. And so I get my 1, comma 2 gives me my x, comma y. Now, b to the first power is just b. So what is the one step I need to do to get b by itself? Square root both sides? Wow, okay. So are we square rooting or are we dividing by the root 2? I think we're dividing by that root 2, right? Because root 2 is root 2 times b. So in order to get rid of it, I got to divide by it. So we'll get b equals 2 over root 2. Okay. Which, actually, if I write 2 as root 2 times root 2, and I have root 2 down here, then I can go ahead and reduce one of them, and I'll get root 2 as my b value. Okay. Now, Eric asked a good question. How do we know to plug in those numbers for x and f of x? Well, those were the points that I chose. 0, comma, root 2, and 1, comma, 2. That's what I chose to do. You could use 3, comma, 4. That would be fine. But I like to choose numbers that tend to be smaller, so then I usually have to do less work to isolate that. Does that make sense? Zero means that the number next to it is my a. Like this is my a value. Yeah. Can you be more specific? I'm not really sure where you maybe are feeling unclear. Oh, okay. So like this part down here. Okay. So when we are dividing by that square root, there's nothing mathematically wrong with this. Like that's an okay answer. But one of the things that's going to be really useful for us sort of in all of the classes that we look at is how do we simplify things, okay? So for example, I know that I can break down any number. So I can say like 9 equals square root of 9 times square root of 9. Because square root of 9 is 3, and then square root of 9 is 3. That part makes sense? Okay. So I did the same thing with the 2. I broke the top 2 into square root of 2 times square root of 2. And then I was able to reduce one of the square roots of 2 on the top with the square root of 2 on the bottom. Okay, cool. All right, Richard, is multiplying by root 2 over root 2 as viable? It is, but sometimes you make the number bigger to then make the number smaller later. So it's viable, but it might not be as efficient. Okay. Cool. All right, so we've got our A value, we've got our B value. We can skip right to step 5, sorry, where we write our whole equation. So we'll have f of x equals A times B to the x. Okay. Can I simplify this? Okay. I am so glad that you said that. So Laura said we could simplify this to be f of x equals 2 to the x. True or false? Okay. So, Laura, to your point, yes, square root of 2 times square root of 2 is 2. Totally valid, okay? But I think Natalia brings up a really good point, which is that the exponent is only for one of the root 2's. It's not for both of them, okay? And so like Eric kind of follows up, don't you have to do the exponents first? 100% you do. So in this case, this might be really tempting to say, oh yeah, I could simplify this. This is a no-go because it violates PEMDAS, or it does not follow the order of operations anymore, okay? So kind of a trick question there. Thank you for being willing to give the answer that I was like, I hope somebody says this, because it's common. We want to make things simpler, and sometimes we cancel too many things, and then we actually are not getting the right answer. Okay, so in this case, we just have that as our final answer. Okay, so there's nothing we can really do to simplify this particular question. All right, so folks, these notes that we wrote here, okay, that I wrote here, I'm gonna post these on Canvas and you'll find them under the link that says 4.1 complete notes, okay? I'm also going to stop the video, and then when I upload it to YouTube, this video will just be for 4.1. Does that make sense? So if you want to come back later to study or just review anything, 4.1, that page is where you're going to find the complete notes as well as the link to the YouTube video. And those should be up within about, give it about a half an hour to kind of upload. That's just a technology issue that I can't really make that go any faster because YouTube has to process the video. But I just want to let you know that I do regularly update things. It's just sometimes it takes a while to process, okay? So I'm gonna go ahead and stop my share here. And I'm going to stop.